We're delighted to be kicking off the seminar this quarter. And what we're going to take the next 45 minutes or so is to brief everybody on the new initiative that the Precourt Institute for Energy has launched called StorageX. And this was a symposium that was held a little less than 2 months ago, so this is still hot off the press. And the title of the symposium is to look at bridging the gaps between science, technology, and economics in energy storage. So ideally, this is a topic that's well suited for the Precourt Institute to tackle. And I think the audience hopefully does not require an introduction to the urgency of the energy challenge, but perhaps what is not realized is that there is an enormous growth needed in the area of energy storage. So we're now reaching an era where renewable electricity can be generated that is competitive with conventional electricity, but it is not available all the time and everywhere that is needed. To resolve this issue, you have to tackle storage. The application of energy storage goes far beyond that of the electricity grid. It goes into transportation, and it goes far beyond that of just conventional automobile transportation, but into electric flights and other exciting applications. And this slide is just to show you all the possible use cases that can be enabled by affordable energy storage. There are many form factors of energy storage. We won't get into too much detail today. There are small batteries, there are big batteries, there are energy storage options beyond battery. And this is really the X in StorageX, is to look at all possible scenarios that will get us to an energy storage option that can make a decarbonized energy system competitive. Unless you've been living under a rock, maybe some of you have, you would have heard that the Nobel Prize in Chemistry last year was awarded on the topic of lithium-ion batteries, awarded to John Goodenough, Stan Wintingham, and Akira Yoshino for their invention of the lithium-ion battery technology some 30 years ago. And this, in the word of the Nobel Prize Committee, is a gift to humanity. I think this is really not an understatement. If you look across this room, the number of lithium-ion batteries probably will be well in the hundreds. And our life today would not be possible without it. But one thing that's quite neat is that although these three individuals are not directly connected to Stanford, we're always very good about pointing their indirect connection to Stanford to highlight our role. And it turns out that many of these innovations trace back to Bob Huggins, who is one of our esteemed faculty in the materials science engineering department, who did pioneering work on battery and related technology in the 60s, 70s, and 80s. And Bob happened to serve as the postdoctoral advisor to one of the Nobel laureate, Stan Wintingham, and also another noted battery scientist, Michel Armand. And if you look at the Nobel Prize statement, it cites several of the early work by Bob Huggins that laid the foundation to understand the chemistry and the physics that underlie energy storage. So this is our small connection to the Nobel Prize. And Stan, being an alum of our department and the university, was very kind to send a short quote to commemorate the launch of the StorageX initiatives. I'll let you read it for a few seconds. And for fun, the symposium happened just, I think, 2 days at the announcement of the Nobel Prize. And that was not timed, but maybe someone had insider news. Not sure. So now, let's go back to the foundational science and engineering. Why are we studying this problem? It turns out it's a very complicated problem. If you look at energy storage, just electrochemical energy storage, which is batteries and others, you have to tackle this enormous range of time and length scale. On the y-axis, we have time. You have to deal with the motion of atoms. That's on the picosecond time scale, all the way to the lifetime of a battery, that's years. Okay, so this is 10 plus orders of magnitude in time. On the x-axis, you have length scale. You have to be able to master working with energy storage at the atomic level all the way to the systems level. So all the way from atoms to that of an electric vehicle, as one example. And at Stanford, we're really good at doing this. We've been tackling this from the synthesis, the fabrication, the characterization, the modeling, the analytics. So this is giving us the ability to look at the problem more holistically. And this is really how the idea of the initiative came about. It was, well, how do we now take it to the next level to span the science engineering from the materials to the devices and then ultimately to the systems level, whereby we can make the largest impact. And we already have a critical mass of people at Stanford. There are more than 20 faculty members involved in various aspects of energy storage, 150 students spanning many departments. You will find many of those faces right here in this room. And I think it's worthwhile to just state the obvious. So why do we need this initiative? What is the purpose? I will tackle it from sort of the strategic sense, and then shortly after, I will tackle it from the pragmatic sense. So on the strategic level, the reason why we need an initiative organized around energy storage is because we recognize the importance of the problem. But also, in order to solve these issues, we have to do something bigger than what we have now. We have to build very strong partnership between university, government, and industry, with industry being a significant emphasis. We want to continue to recruit the best talent to come to Stanford to work on energy storage. We want to be able to enhance the interaction between faculty members already at Stanford. There are many people working in an isolated fashion, but there is an opportunity to bring everyone together. And then lastly, we want to be able to go beyond what we can do as individual principal investigator, do something bigger to build translational facilities and multi-PI labs so we can do bigger things. It's my pleasure to introduce the people behind the initiative. Of course, you'd have met my colleague Yi from the Material Science Department, but we also involve many other faculty members as well. Simona Honori in Energy Resource Engineering, Fuguo Cheng in Aeroastro, and various other members of the Precourt Institute have been involved to get this off the ground. As I mentioned, the symposium that launched this effort was just a little less than 2 months ago. The symposium was also supported by 4 schools to indicate the cross support that we're receiving across the university. The Precourt Institute, of course, the School of Earth, Energy, Environmental Sciences, Engineering, and the School of Humanities and Sciences as well. And everybody pitched in to make this event happen. Now, all of this effort were meant to coalesce not only the people at Stanford, but also people outside of Stanford. So we were very excited to announce that we have assembled a range of industry partners that represents various parts of the vertical supply chain as well as the horizontal market. For example, from materials companies to battery companies to OEMs and electric vehicle manufacturers and integrated energy companies to create an initiative that can bring the type of insights from industry and then provide it as a guiding feedback for researchers doing work at Stanford. So now, let me try to get into some specifics here. So lithium-ion batteries specifically just received the Nobel Prize, so you might think the work is done. But it's hardly done, actually. It's extremely challenging. So one thing I did not read out is the size, the economics of energy storage. So we're talking about, in the next 15 or so years, the market rising to over $1 trillion. It will be the largest market of a single technology. It's approximately the size of the silicon industry today. There are still many challenges. Perhaps the most significant challenge is how do we sustain the cost learning curve of batteries? 10 years ago, a kilowatt hour of battery, of lithium-ion battery, would cost you somewhere on the order of $1,000. Today, maybe $120. So it's a factor of 8 just in 10 years. But this has to continue to go down. We're still about 3 times more expensive than that is required for widespread adoption of electric vehicles. We have good adoption, but widespread adoption to have all of your vehicles becoming electric, this is still very far away, and this is primarily limited by the cost of energy storage. If we want to use energy storage on the grid, the cost would have to be 10 times less expensive than today for lithium-ion battery. So we must innovate to find new chemistry, new device architecture so we can reach the type of cost that would enable this. So we're 3 to 10 times off. Okay? So we cannot be complacent. On the technology side, the current specification of the batteries are also lacking. Yes, they are enough to drive an electric vehicle for 300 plus miles, but if you want to have it really be competitive on the transportation sector with fossil, then you have to be able to meet several challenges. For example, can we recharge the battery at the same time scale as refueling the car? Can we start looking at lightweighting the batteries furthermore to increase the efficiency? And there is many work looking also at the life cycle cost of using lithium-ion batteries. The CO2 cost of manufacturing the battery is also very high. So there are many advantages to making the battery more energy dense, which means we store more energy per weight or per volume. And this will continue to be one of the significant technical driving forces. We want high energy density, high power, so being able to deliver the energy very quickly, safe, and long-lasting. Long-lasting is perhaps one of the biggest challenge for battery adoption for the electricity grid, because you will have to have it work for a quarter of a century at the minimum for it to make economical sense. So we're still very far off from that. If you want to go to $1 trillion market from the 50 billion that is today, you have to solve significant scientific challenges in scaling up. Many of you may have heard how many gigafactories we have to build in the next 10 years just to satisfy the demands for electric vehicles. Those numbers are real. So how do we continue to innovate the scaling up process so we can make it faster and less expensive? Ultimately, batteries will fail, and we have to do something with it. And today's lead-acid battery is possible because you have a 95% recycling rate. I don't know what you do with your lithium-ion battery, but after you give it to whoever you give it to, there's really nothing beyond that. So as the adoption of electric vehicle rises, we have to address the issue of the so-called circular economy through not only the recycling, but also the reuse of battery repurposing and potentially regeneration. We will hit a bottleneck very, very soon if we don't look at this particular aspect. And then finally, it's always important to mention artificial intelligence somewhere. So we mentioned the following sense. The R&D pace is slow for batteries. It is a material-based technology. We need chemistry. And it's not something you can just code up and it works, right? You have to actually make it. And the typical development time for lithium-ion battery technology is 3 to 7 years. And artificial intelligence in informatics has an important role to play to accelerate the pace of research and development. That's one of the main goals as well. So these 5 things are, I would consider, technology agnostic goals for energy storage. Doesn't matter which one you want to do. Doesn't matter what the X is. You will have to solve every single one of these in order for us to make a greater penetration of energy storage and hence renewable electricity. Now, let me talk about the initiative in some detail. So I'm going to try to establish what we're trying to do differently. You heard, and many of you know, we have a vibrant energy storage community here at Stanford. And this is how we've been approaching things. We take what's on the left of this screen, which I call the academic research pillars. We're really good at gaining fundamental understanding. We are really good at designing materials, making them. We operate many big science facilities. And then we're also very good at embracing new directions quickly, like machine learning. But on the other hand, if you look at industry research and development, they do things a little bit differently. There's a great emphasis on prototyping and scaling up. The optimization is exhaustive, relentless, one might say. One always cares about how the technology is integrated into the whole system. And then you have to think about the business model, the cost, the life cycle, all aspects of it. And this is not simple. And what we're trying to do in this initiative is to empower the people at Stanford, the faculty, the staff, the students, the postdocs, and to get the best of both sides. In a pre-competitive setting, we're not trying to compete with industry, but we're trying to take what we do best in academic setting, but to siphon elements in a pre-competitive setting from industry development so we can merge it. And the main outcome that we hope to have is to de-risk the technology for scaling up and commercialization, to be able to take something that we have, say, invented or discovered here at Stanford and be able to turn it into a reality. So now you have a general sense of our guiding principles and the strategy. Let me now show you a couple of highlights of what we have been doing so far. This is pre-StorageX. And then I will show you a couple of case studies of how we can expand and integrate. And then E will show you additional examples from his research that ties everything together. So in terms of fundamental understanding, as I mentioned, this is one of our key pillars. We're really good at understanding the detailed mechanisms of things. For example, on the left here, these are the first atomic resolution images of lithium metal, which is a very promising material for high energy battery that could be 10 times of the energy density it is today. This is from E's group. And this is also the first atomic scale image of the passivation layer that protects the lithium metal from further corrosion. On the right are examples from my group that shows that we have also the ability to understand how lithium is inserted and removed from battery materials, not only at the single particle level, but also at the porous particle level. So you can see these are advanced measurements of the chemistry, the dynamics, the microstructure. You can see this fly through. That's a single battery particle that's about 10 microns wide. And the color you see is the distribution of lithium. So we have been able to answer some very basic questions about where the lithium are, how they get in, how it is passivated at the atomic level, at the mesoscale level, and at the microscale level. Another example of recent success in the energy storage area is the application of machine learning in two ways. On the left, I'm highlighting the work by my colleague Evan Reed, who has been using machine learning to accelerate the discovery of materials. So as we can appreciate, there are many millions of materials we can use for batteries. So which one is the right one? We don't have the resources to examine all of them. So one can take a standard approach of using computation and quantum mechanics to predict the right composition, but even that takes a long time. It takes about 4 weeks to make one prediction. But if you were to combine that with some degree of machine learning to look at the relationship between the data, then you can get it down to less than 1 second per prediction. So that can greatly accelerate. And this is an example of searching for solid electrolytes. So these are solid rather than liquid electrolyte, which are not flammable. And these are considered for the next generation lithium-based batteries because it can be potentially safer. So this can help the acceleration of discovering new materials. On the right, it's just a cartoon, but highlights one of the recent examples where machine learning can also be used to forecast the lifetime of battery. One of the toughest things with batteries is that they are hard to break, which means if you want to assess how good the battery is, you have to run it to failure. And that means sometimes many, many months under accelerated settings. If you don't accelerate it, then it's many, many years. And machine learning can actually now also help us, for example, to predict the future behavior of the battery with great deal of accuracy. For example, in this work, we were able to take just the first few cycles of the battery, just the first day of operation, basically, and predict its lifetime out to many thousands of cycles. So this can really accelerate the R&D pipeline for battery technology by reducing the time needed to evaluate the battery. So these are just two examples. Now, trying to glue everything together, we at StorageX identified several cross-cutting topics. These are topics which don't have just one, but several components. For example, accelerated testing and validation, advanced sensing and diagnostic, battery use, I already talked about, fast charging, so on and so forth, even looking at resource availability. These are the 8 core topics of StorageX that we're trying to engage our industrial partners and also our colleagues trying to address. I will give you 2 quick examples of how integrated these problems are. So this photo here shows you a electric car taxi driver in China that is waiting for their car to be charged. So these are downtime and time that they're not generating revenue. So one solution to this is to make battery charging faster. Today, the battery charging time to maybe 50 or 60% can be as little as 45 minutes, but to charge it to 80%, it will take about an hour and a half. So this is about 10 times to 20 times longer than the refueling time of a gasoline car. If you think about the amount of power that is required for charging, we're talking roughly, if you have a 100 kilowatt hour battery pack, you want to charge it in 5 minutes, which is roughly the refueling time. You're talking about 1.2 megawatt, and that is roughly 1% of a Boeing 737 taking off. Well, not the MAX right now, but just the regular 737. And if you look at the entire flow of energy, you have to go from the grid, where the electricity is being supplied from, to the charging station, to the vehicle, to the battery pack that's in the car, to the individual battery cell that's in the battery pack, and then you have to get it to the material that does the ultimate heavy lifting. So you have to manage this flow of 1.2 megawatt across this, times however many cars are charging simultaneously. And the type of problems are quite significant. You have to manage the grid, because this can cause significant disruption. Charging electronics would have to be made very efficient. On the vehicle level, you have to optimize how the energy is delivered as a function of time. You have to engineer the battery pack. There are discussions of using sort of temporary reservoirs to hold the energy quickly, such as a supercapacitor. You have to manage the temperature very carefully. Once you get it into the battery, you have to think about how far the lithium would have to travel in order to minimize gradients. And obviously, the materials will have to be able to handle the type of rates we're talking about. And there are also alternatives. You can think about battery swapping, for example. Rather than charging the battery, you pre-charge it and just swap it in and out. So these represents the complexity of the problem. So many of us are now working on this in order to enable fast charging. I should mention that at our symposium, we had a speaker from Airbus who told us that for aviation, this is even a greater problem because the time a plane spends on the ground as time is not making money, and that's as little as 1 hour. And this is another problem that the aviation industry is tackling. I mentioned recycling already, and this is one aspect that is extremely important that we are tackling. We call it battery reuse, recycling, and regeneration, looking at the 3 possible cases of what you do with the battery when it comes out of surface from its primary application. So for example, the first life use could be electric vehicle. After you have reached the end of life, so this could be 80% of its initial performance, 70% depending on which car manufacturer it is, you have a decision to make. You have to think about, do I recycle it? Do I boil it down to the raw material and get the expensive things out? Do I repurpose it for something else? That's called reuse. That could be, for example, for incorporation into larger systems like storage for wind and solar. And we can also think about later use as well beyond that. So what are the issues involved here? We believe at the heart of this is a performance and valuation model. So at every decision point, we're trying to assess how much is each one of these options going to bring value to the user. So for example, at the end of use for the car battery, is it worth $10, $100,000, $1,000, $10,000? We actually don't know very well because depending on the next application, the valuation can change. So we're taking a very comprehensive systems approach here to look at, for example, the data behind it. So can we make predictions about how the battery will perform in its next cycle, next use? On the system side, we also have to think about how do we swap these batteries in and out? How do we make it more universally changeable? If you want to rejuvenate the battery, well, how do we introduce the regeneration aspect into it? And on the materials level, we also have to ultimately think about the cost of recycling. To boil things down to the most expensive element, in the case of lithium-ion battery, it's most likely cobalt, and that is a very inefficient process as well. So all of these are being explored right here at StorageX and at Stanford. So let me now hand over to Yi, who will show you and share with you some of our success stories taking these academic curiosities all the way to commercial realizations.
Thank you, Will. So, well, thank you. This is a very, very nice overview of StorageX. I think in the next 20 minutes or so, let me use one example to show you our learning curve. And from the learning curve, we want to do better inside StorageX. But let me reveal one information first. I look back when Stan Whittingham won the Nobel Prize, I say, oh my God, the first paper he published leading to his Nobel winning award was published in 1976. That was the year I was born. It took really a long time to get there. Right? John just turned into 97 years old this year, 97. Lithium made people live longer. That's a good news. But lithium battery is actually very, very challenging. You better live very long in order to achieve somewhere. So 96, intercalation mechanism, and Stan's science paper. And in that's 1976. And in 91, that was the first commercialization product of lithium-ion batteries. So that's roughly about 15 years. That's the type of cycle you should expect. 15, 20 years for hardcore materials technology, from initial invention to commercialization. Inside StorageX, we know one of the biggest challenges we want to address is how to increase energy density of the batteries. Per charge, you can run for longer distance, 500 miles or longer. That's something we want to achieve. We want to really, make the technology go to that level. For about a decade, a little bit more than a decade after I joined the faculty, starting the research on lithium-ion batteries, some of the chemistry we want to work on different from 1970s, right? The existing technology, graphite intercalation, lithium cobalt oxide, and so on. We want to look at silicon, for example. That's very high capacity. We would look at metallic lithium anode. We want to enable solid-state batteries that's safer. And we want to use new type of materials, polymer that's very resilient. For example, this is a needle, try to punch through this polymer, but it's so resilient, this needle cannot go through. We want to use this type of polymer to prevent lithium dendrite formation to enable metallic lithium. This is the type of chemistry, the new material we want to enable. It's very challenging. However, if you could do that, this is the pathway you can get to, right? We are roughly somewhere around 250, a little bit higher than that right now, 1 hour per kilogram of energy density per unit weight. Can we go to 400, 500 and more? Then you can enable the possibility of 500 miles driving range. But there's a lot of problems right there we need to solve. I want to share with you the story, back to a decade ago until now. What do we learn? How can we do better in the future to let the academia and industry to work together to speed up this process? The example I want to share with you is the silicon. Coming back to silicon, I'm still working on these materials. It's been more than a decade. But silicon is a candidate that can replace graphite, carbon as the anode of the batteries. It has the capacity that's about 11 times of graphite. And imagine if you can put silicon into your batteries, it can boost up the amount of energy it can store because it stores a lot more charges, a lot more lithium for a given weight. However, the volume expansion is very big. When silicon expands, they can break. And also, the interface is not stable. So these are really, really challenging problems. Not knowing how challenging that is, about 11 years ago, 12 years ago, I started to work on it, published the first paper. And that just only started all this learning of how challenging the batteries could be. At the time we didn't know. I only know, well, I can solve one problem. Let's go and doing this a little bit, just a little bit by a little bit, just keep learning. It's actually very, very hard. So back in 2008, so I published this first paper using silicon nanowire by thinking nanostructures are small enough. They could solve the expansion and breaking problems. Actually, it did. It solved the breaking problems. Let me share with you one of this video, in-situ video, inside TEM. This particle in the center right there is 800 nanometers in diameters. Now I'm charging lithium going into this particle. You see the volume expansion is taking place. These particles are shaking because you zoom in so much, magnification is very big, and the vibration will show up inside transmission electron microscope. And pretty soon you're going to see this particle is broken. Because lithium coming in, this particle keep eating up a lot of lithium. This silicon doesn't know this particle is already full, just keep eating it. So at the end, what happened? Fall into pieces. So, and using nanotechnology, we showed this could be solved by making the structure smaller so they do not break, they do not accumulate too big of stress to be broken. We identify the critical breaking size. This highlight the value of fundamental research in university. Once you know this critical breaking size, you know what size of particle you need to use to build a battery electrode so they don't break anymore. This turned out to be guiding the industry now. All the battery company try to say, well, what's the particle size they need to use? Basically, those are the particle size, 150 nanometers or smaller. For the particles, nanowires about 300 nanometers or smaller. So this learning keeps going. Along this process, right, we identify so many problems we have to solve. It's endless. Well, luckily, this is also the process. We see, that's why we need government. We need a university, government, industry working together. There's a different perspective. If you're working at different segments of the problems, the earlier you know, the better. That's number one, the value. Because industry try to optimize, deliver their batteries to you, they can see all the problems once they deliver a real product. If you know those problems coming back, you can speed up the innovation. And also, not only that, also from the funding support standpoint, we need a continuous support. We know funding cycle go through, government usually 3 years. If you can harvest the funding support from our Stanford side, GSAP is a great example, funding some of this early research, later picking up by Saudi Arabia, the CAUS, the university award, providing this funding, and later picking up by the Department of Energy. This actually provide support about 10 years to continuously advance the understanding and coming up solution to support that. Within Storage X, we want to have a support mechanism to really get some of the new ideas to start and also get some of the really good ideas later picking up by the industry. So over the past more than 10 years, about 12 generations of design, I wouldn't bother you about that. But this is on the university research side. But indeed, in order to make a challenging materials like this to go into the industry to be used, and industry needs to pick up. So 2008, I didn't know how challenging a battery technology could be. I started our company called Amprius. So I was thinking, average, can take 15 years or 20 years to commercialize a technology. Maybe at Stanford right here, it'll be a little bit smarter. We can make it 7, 8 years. But I was completely wrong. It actually, looking right now, 2008, I found the Amprius, 2007 technology is invented. Today, this year, 2020, 13 years now. So I'm about hitting to the 15 years mark. It actually took very long time to get there, and also a lot of money as well. Well, let me share with you. So after the Stanford research, what happened? And Amprius has a very dedicated team to develop the manufacturing technology to make those wires. If you visit my lab, you go into my lab, right? How we make silicon nanowire is a tube furnace like this big. A quartz tube, 1 inch diameter, making a coupon size. The silicon nanowire material, we build a corn cells, we publish a Nature nano paper. It's very actually easy compared to industry. Industry need to make a real product with the right performance and the cost. It's very, very challenging. I would say this with a little bit of luck, actually a lot of luck. Now Amprius is getting into, this is not tube furnace anymore, right? This is almost like 15 meters long, row-to-row fabrication line of chemical vapor deposition. It's also a new type of manufacturing technology battery industry didn't use yet, does not use yet. Then to need to validate that. So over the past decade, this was validated slowly until now that you are seeing those row-to-row, really big row, the black color of silicon nanowire growing on the metallic foil. This is also the opportunity to innovate in the whole manufacturing scale up. Within Storage X, we talk about taking the idea to a scalable solution. How do you do that? And this might be one of the examples, I would say right there. Traditionally, how do you make a battery electrode? You take the particle, you mix with slurry, put in a polymer binder, with solvent, you do the coating. After the coating, right, you do the calendaring, you heat it up, and all this process, multi-step. Now, just those multi-steps are gone. Just one step, the foil in, foil out, and making the whole electrode. So up to now, the silicon wire technology deliver, and I highlight in the red right there, the watt-hour per kilogram, 430 in that level of watt-hour per kilogram of the batteries. This is a unit change. When a university, when we work on certain new materials, we use milliamp hour per gram. That's the charge per weight. But when you go to industry, milliamp hour per gram, you are not delivering that. You are delivering energy. It's actually watt hour per kilo. Just simply this unit change from milliamp hour per gram to watt per kilo means a lot. You are doing something real. That also means there's probably 20, 30 big problems already solved. And I hope those problems in university research, we can see those problems earlier. That's why building up this industry, university partnership is so important. There's some problem we don't see within university research, but those are actually perfect for university research to tackle. We can de-risk the technology in a pretty competitive sense and speed up the innovation. I want to show you a video. In my lab, my graduate student doing this hand by hand, right? Now let's look at this automatic silicon nanowire stacking line that I stole from the Amprius CEO with his permission to show. And it actually now can, roll this silicon nanowire row to row and actually stack up this layer by layer using automatic machine. It's very small at this moment. There's still a lot of hard job to do to do the manufacturing much faster. So this has been delivered to Airbus, partner with Airbus. So then I say, well, silicon is an example of how we do materials innovation. The holy grail is really lithium metal right there. Lithium metal combined with sulfur, combined with other cathode, even higher, much higher energy density. And that's the holy grail. But there's huge problems right there as well. Indeed, before 1970s and the 1960s, when people think about lithium batteries, they didn't think about graphite, didn't think about intercalation. They want to use metallic lithium first to be the anode. However, it failed. It's just too hard. Nobody knows how to solve the problem. We are running out of choice. After silicon, lithium metal will need to step in. So many exciting problems to work on, almost like impossible to solve. I think I still having the next 30 years to solve the problem. Will have more. He has 40 years. He's younger. So we'll work hard to address this problem. So we have a team right here. This grand challenges is really exciting to bring the team together. On the lithium metal anode side, after Steve comes back to Stanford, actually Steve and I have a chat and also a few other people. I said, what's the most exciting problem you want to solve? Steve said, lithium metal. I said, for me too, let's work together. So we work together, come up new solution. I won't go into the details. And also bring in the polymer expert, Zhenan Bao. Zhenan is a magician on polymer. It's all type of polymer coming out. Its property can help solving these problems. So with this as an example, now let me zoom out a lot for storage X and see in the whole Stanford energy landscape, right? And we know this has been planned since GSAP time, pre-core. Now, so many areas of energy come together, folded into pre-core institute. So we don't work in a vacuum. We work actually within a really large number of talented faculties and students. And storage is one part of the solution to a very, very big problems. This goes in parallel with other initiatives, such as the natural gas initiative. We are learning quite a bit from natural gas initiative. How do we run storage X? And we need to learn more because we were just born 2 months ago. And also very strong connection is actually with bits and watts. Storage, not only for the cars, but also for the grid. And this very strong partnership will allow us to guide the technology development, guide the whole system level understanding. We told you about when you charge the car, 5 minutes, the 100 kilowatt hour of battery require 1.2 million watt of power. These batteries in the grid come hand in hand. And also, what's also very important is the financing part. I was telling you that, just a funding support part. For each faculty, we know this is super important to keep stable support. Once you have a technology going out, and you need to put into the economic environment to see what else, what more you need to solve. So the partnership with the sustainable financing is very important. As well as with the industry, this is the place. Our students, our postdocs, our faculties are highly entrepreneurial. Starting a company, translate, move the technology out of the campus and go into the real world. So there will be quite a bit of partnership as well. I will expect multiple exciting, probably new startup can come out of this initiative. So let me end my slide by doing the advertisement for Sally and Arun about the Stanford Global Energy Forum. This is very, very exciting event. 2018, the first event was huge success. And I know outside people keep asking, when is the next event coming? Internally, we are really looking forward to the event coming up in May 2020. With that, I will stop, and Will and I will be happy to take any questions you have.
Great. Thank you both for sharing your vision of the room 20 storage act style. We really appreciate it. We now have time for some questions. I do have two more announcements. One for the audience in general. Thanks to Sarah Weaver and others, we are going to do a 300th energy seminar celebration right after next week's energy seminar, right upstairs. And Sally Benson and Roland Horn and I and Jeff Kostaff, maybe Lenore will come too, who have all been involved in putting it together. So I think it should be a great celebration, and we hope as many of you who can will attend. Secondly, our course assistant for the project, for the seminar, Vivan Kalkani, is stuck in India for a couple of days, so he missed today. So we're not actually doing attendance today. Professor Chueh is willing to do a student discussion group if you want to get that out of the way. So we'll poll the students right after the class to see if anybody wants to do it. So each student has to attend all, except for one seminar, write a 2-page paper at the end, and attend a after-seminar discussion group. So if you're interested in talking to Professor Chueh, just let us know right afterwards. So with those two announcements said, let's go to the audience, starting with students for a few questions. Any takers? For students, job opportunities, research opportunities, student research opportunities, career guidance.
Yeah, I was just wondering, I understand that it's, that you're not actually, well, okay, yeah. I understand that you're not, it's all hypothetical right now, and you were talking about, like how expensive it might be, and I was wondering when you would break even, like as a, like right now, the model that you have.
Like, can you repeat the question? Break even for it's for the amperes?
Yeah,
or
as in like break even, like the like the costs won't like outweigh the profit.
Okay,
I mean,
good.
Yeah.
I was thinking
like
storage X break even,
yeah.
so
Yeah.
would be very hard. We only spend money. So I think we are now at the point of breaking even. So indeed, Amprius is considering the exit at this moment after actually a decade. So it's the time. Well, but let me mention more about this. The cost of the battery is the nanowire one. I'm telling you, the cost is still high. So it only fit into certain market at this moment. That's for the drone market. That's why Airbus made the purchase. It's not yet for transportation. And get to the level Will mentioned, $120 per kilowatt hour. We are too far away. So we'll need to scale up that CVD plant, multiple line with this learning curve. I don't know how many years down the road. We might get there. We might get there.
Other questions, comments, students? I got one back here. Why don't you go?
Hi, so you guys had talked a bit about lithium-ion technologies, but also mentioned that sort of the framework for storage X is agnostic to the technology. I was curious, as it's growing and changing in the next couple of years, if you guys are planning to try to expand out and include other technologies, or if you're more focused on pushing lithium-ion forward as fast as possible.
Well, I think to get started, we are focusing on the segment that has the largest immediate term growth potential, and that will be what we call electrochemical energy storage, EES. And that includes batteries, but also other kinds. So you are familiar with lithium-ion battery, but there are also other types of battery, for example, flow battery for grid energy storage. So those are the center of our immediate focus. But beyond ESS, you can also look at, EES, you can also look at thermal storage, you can look at other chemical storage, and there are also just even simpler ones, mechanical, pump hydro, and not all problems exist at all of the scales. So for example, if you talk about pump hydro, the problems are very different, different sorts of problems. So we do hope to start to weave those in as time goes on, but our immediate focus is on electrochemical technology. I think that is the one requiring most immediate attention, and that can be split into your lithium-ion battery and related technology for transportation, and then something that's much lower cost for the grid.
I put a slide up. Indeed, yeah, we consider all type of storage, not just the electrochemical, the battery-based. There's a thermal, for example, on there as well.
Question back here.
Hi. What kind of batteries application does Imperius produce for? Like phone, renewable energy? And,
so starting, Imperius, this high energy one, because the cost is not that low yet. So it got to be the high margin one. Starting a company is start to learn about all these words important. I used not to think about high margin in academia. Is more of the portable application. The one giving you quite a bit of, the market is the drone, particular commercial drone. And it requires very high energy density, and very few companies can make. That will be the first one. And then next one will be consumer electronics. The last one might be the car. The grid is still far away for this type of technology.
So what company should we look out for battery application of renewable energy storage?
So the question's great. I know you guys have some work going on.
Maybe in the discussion session, let's chat about that. Yeah, yeah. It's a much longer conversation.
So you guys mentioned that you're off by a factor of like 3 to 10 for widespread application of electric vehicles on the road. I was interested in what is your guys' time scale for when we can see a future where electric vehicles are on the road, and also which companies are going to be the ones that are going to pave the way for this future, because Tesla is doing all the work. I'm wondering, how do you guys think the academic and government play into this?
So I think first you can delete the government subsidy, right? So that will give you a $45,000, $50,000 Tesla car today. So if you think about something like the Toyota Corolla, that's under $20,000. So that already tells you the delta you have to work with. So I think indeed it's challenging. I hesitate to put a time scale to it. I guess the default answer is always in 10 years, but 10 years ago you probably would have said 10 years anyway. So I think predicting the time scale is always difficult, but all major vehicle manufacturers are projecting by 2040 widespread conversion to electric vehicles. So it's really a matter of when. I think the battery technology costs will continue to come down. They will reach a floor because right now about 35% of the cost is already raw materials, and those are only climbing, they're not falling. So that sets a boundary.
Yeah, let me add how to think about this problem. There's one perspective we shouldn't forget. We need to look at the lifetime ownership cost to a car. If you own an electric car, you don't burn gasoline, and electricity cost is low. And the maintenance, the oil change for electric car, really nothing right there. Maintenance, driving electric car for a number of years right now. I never go do a service for my electric car yet. So my estimation is, only simple estimation, when the electric car, the price is about $35,000. And to the owner, it's equivalent to a gasoline car, probably about $20,000. The cost of ownership, including everything. So 35K is the number I'm looking at. If it's 35K and below, I say electric car is already as competitive as 20K of gasoline car. That's how things will fly completely.
Great. I think we're just about out of time, so let's thank our speakers, Will and E.